through one more of these examples where we try and get all the information we can from first and second derivatives and put it together to sketch a graph. I've done some of the work for us in this one just because I think we've hopefully seen it enough. I've given you your function, but I've also given you your first and second derivative, so you don't have to work through that simplification. But this is an interesting one. Okay, so notice we're supposed to find the intervals on which the function is increasing or decreasing. The function, this is the cube root of x squared, and this is the cube root of 4 minus x. That has a domain of all real numbers, so there isn't anything that we can't square or cube root or subtract from 4. So all real numbers. However, the derivative does have some domain problems, so that's what's really interesting about this one. Okay, so if we want to know when the function is increasing or decreasing, I think the easiest way is just to make a first derivative sign chart. So here's my first derivative. I need to figure out when it's 0 or undefined. So it's 0 when the top is 0, which will happen when x is 8/3, and it's undefined, so this is f prime equals 0, and this is f prime does not exist, if the bottom is 0. The bottom is already factored for me, so if I'm thinking about setting that whole thing equal to 0, that's going to say either the 3 times the cube root of x has to be 0, or the 4 minus x to the 2/3 has to be 0. Here, the cube root doesn't make a huge difference. You can solve if you want, divide by 3 and then cube both sides. But really what I'm seeing here, even without doing that, is that the only way to make this 0 is if x is 0. And here, the only way to make this thing 0 is if x is 4. So again, if you want to crunch through those steps and be sure, this one, you could raise both sides to the 3/2 power to get rid of that, multiply powers and they would cancel, and then you could add x. Okay, so I'm interested in x equals 0, x equals 4, and 8/3, which is 2 2/3. So if this is 2 in the middle, right here, okay, 8/3. This was where it's 0, this was where it does not exist, and this is where it does not exist. Okay, so I'm going to need to test that derivative. The 8 minus 3x over 3, it's the 1/3 times 4 minus x to the 2/3, to figure out when it's positive or negative. So I'm going to try a -1. I get 8 minus 3 times -1, so 8 plus 3 is positive. On the bottom, I have 3 times the cube root of -1. Cube root of -1 is going to be negative. And then I have a 4 minus -1, so 5 to the 2/3, which is going to be positive. And I think I'll just point out right now that that 4 minus x to the 2/3 is actually always positive, except when x equals 4 and it's 0, because the 2 on the top of that fraction means it's squared. Okay, so positive over negative times positive. That's going to give me a negative. I'm going to test in here. The 1, 8 minus 3 is still positive. Cube root of 1 is positive, 3 times that's still positive, and then we've already said the other one's always positive. Okay, and then I could check 3, so that covers this, this, and I get this, and then out there. Okay, so at x equals 3, I get 8 minus 9, so the top is finally switched on me. The 3 times the cube root of 3 is positive, and the other one's always positive, so I am back to negative. And then out here I could test a 5, and I could say 8 minus 15 is negative, cube root of 5 is positive, the other one's always positive. Oh, did I get a bounce? I think I did. Yeah, and that actually makes sense to me, and I'll show you why. This 4 minus x is raised to the 2/3. So what happens here is at each of these spots, one of the factors switches signs. So in this first one, the cube root of x switches from negative to positive. In this second one, it's the top, the 8 minus 3x that switches. And in this last one, the one that's left that could possibly switch is that bottom factor, but because of the square, it doesn't switch. So that's why we get that. Okay, oh, except, look, I wrote a plus. Ignore me. Okay, so it goes minus, plus, minus, minus. So I'm going to say it's increasing from 0 to 8/3, else, but we need to list this carefully, everywhere else except at 8/3 and 0 and 4. At those, there's either a flat spot or something weird happening. So it's decreasing from negative infinity to 0, and then from 8/3 to 4. And notice I am listing this separately to make sure I leave out the 4, and then from 4 to infinity. Okay. In the next part, again, I've done the derivative work for you just to save you from crunching through. It's a little messy to simplify, although doable. So if you want some practice, there's some good practice on funny powers. The second derivative is negative 32 over 9 times x to the 4/3 multiplied by 4 minus x to the 5/3. And we want to figure out, using that second derivative, when is it concave up or concave down. So I'm going to do the same thing, make a sign chart, but this is a sign chart for the second derivative. The second derivative tells me about concavity. Okay, so f double prime equals 0 only if the top of the fraction is 0, which is never, so that is not happening. F double prime does not exist when x equals 0 and when x equals 4, just like before. So even though the power's changed, it's still just those factors in the bottom that we're trying to get to be 0. So we're interested again, and I'm going to try and keep these kind of lined up, in 0 and 4. 8/3 isn't quite so interesting, but I'm just going to mark it off so that we can follow all the way down. These are kind of key points so far. And pretend that hit 0. I need to test in between, except not in here. So I need to test between 0 and 4, to the left of 0 and to the right of 4. So I'm going to test negative 1, and this time you're testing f double prime. I'm checking concavity, so that doesn't come from the function or the first derivative, it comes from the second derivative. So this time the top is always negative. The 9 times x to the 4/3, always positive, so it's really just this 4 minus x to the 5/3 that we're interested in. When x is negative 1, that's 5 to the 5/3, which is going to be positive. And just to make sure people are okay with this, the reason x to the, well, I shouldn't write it there, x to the 4/3 is always positive is because that's the cube root of x to the 4th, and x to the 4th is always positive, so its cube root will stay that way. Okay, and then somewhere between 0 and 4, I'm just going to snag 2. And again, testing the second derivative, so the top's always negative, the first factor is always positive. 4 minus 2 is 2 raised to the 5/3, still positive. So we have a minus and a minus. And then I'll try out 5. Top's negative, first factor is positive. And then 4 minus 5 is negative 1. And when we raise that to the 5/3 power, those are all odd, so that's going to stay negative. So finally we get a change. So it's concave down, concave up. So let's say concave up from 4 to infinity, and then concave down from negative infinity to 0, and then we want to leave out 0, something weird's happening there, and from 0 to 4, it's concave down again. Okay, so we have definitely something interesting happening at 0 and 4. What's happening at 8/3? 8/3 is interesting, but it's nothing too unusual. At 8/3 we have a flat spot, and the function switches from increasing to decreasing, so that's a maximum. Or you could say we have a flat spot and it's concave down, so that's a maximum. So I do have a local max at x equals 8/3. And then let's check these other critical values, right? So our critical values were 8/3, 0, and 4. So at 0, what do I want to say here? The function is defined everywhere, so there is a point at 0. The derivative switches from negative to positive, so it's decreasing and then increasing, so that appears to be a local min. Because the function is defined everywhere, the derivative being undefined doesn't mean that there's an asymptote or there's a hole. What it means is there's a corner or there's a vertical tangent, one of those two things. So here, because it switches increasing to decreasing, it must be a corner. So at x equals 0, there's a corner. And then at x equals 4, it's decreasing and then decreasing again. So I'm thinking that's maybe the vertical tangent line. It could be a corner as well, I guess, decreasing and decreasing. There's ways for that to happen. But that's a neither. Inflection points. Okay, so this is kind of an interesting one because here we are concave down and then concave down, so we don't get a switch. And then here, this is a funny one, and I actually don't feel that picky about it. I've seen it both ways. So when your derivative becomes undefined, I think I would still call it an inflection point. The concavity changes. There is actually a point on the graph, so it was just an asymptote. I wouldn't call it an inflection point because it's not a point. But here, there is a point on the graph, and it changes. So I would say we do have an inflection point at x equals 4. Corners. I think sometimes people are fussy about whether or not they want to call corners inflection points, and I would be fine with it. The concavity changes, I'm good with it. Okay, so we're supposed to try and sketch a graph, and I'm just going to sketch it below on this side. Oh, maybe, can I get it so you can see? I'm going to try. Okay, so x equals 0, that's going to be my y-axis. And I definitely want to know what's happening at 4, and what's happening at 8/3, and what's happening at 0. Those are all kind of key points because it should be vertical. So that, and that, and that. Okay, so we have an inflection point at x equals 4. Let's get some y values for some of these points. So my original function was m of x equals x to the 2/3 times 4 minus x to the 1/3. So this local max is at x equals 0, and when x equals 0, y is also 0. So it's really 0, 0. So actually my dot was okay. 0, 0, and that's a min. And then 8/3, oh, I'm not delighted about that one. 8/3, 4 minus. Okay, hold on, trusty phone calculator. Oh, you know what? I have a regular calculator today. I finally remembered to get it in batteries. Okay, so we want to know what 8/3 to the 2/3. You need parentheses around that power. Oh, actually I don't, because I brought the smart calculator that puts it up there. If your calculator doesn't pretty print, you will need parentheses. And then we need 4 minus 8/3 raised to the 1/3. Oh, again, I didn't really need them, but that's okay. So about 2.1. So this is in the ballpark of, what is that, 2 2/3? And then 2.1. Okay, so that's 8/3. Okay, let me just see what the other one is. When x equals 4, oh, actually that's another easy one. It goes through 4, 0. Okay, so let's just say this is 1, 2. So just a little higher than that. Okay, so there's 3 points. Global behavior is good to look at as well when x gets really, really big. So say we have a million to the 2/3 is still a really, really big number. So this is getting really, really big. And then 4 minus a million to the 1/3 is a really, really big negative number. So we're getting a really, really big negative y value when x is really big positive. If x is really big negative, let me think about that. I think that is actually a little different because there's a second power here. This is going to get really big positive. And then 4 minus, say negative a million, that's positive. So that's going to stay big. So it's going to head off to positive infinity as x gets to be a big negative number. Okay, so from positive infinity, I know there's a minimum at 0, 0. And if you look back up, hopefully we can see this. Yeah, I think we can. We went decreasing and increasing, and we were concave down and then stayed concave down. So decreasing, concave down. Here, let's see. There's the 4 shapes, right? There's this and this and this and this. Okay, so decreasing, concave down is this one. So we're coming in, and the function is, let me move my arrow a little, decreasing and concave down, and then it hits 0, 0. And it switches to increasing, but it stays concave down, which is, oh, you can't see it, this shape right here. So decreasing, concave down, increasing, concave down. So I think it is, in fact, a corner that we're hitting there. And then, let's see everything stays the same until we hit 8/3, and at 8/3 we had a local max. So we hit, we hit a flat spot there, and we stay concave down, so this goes off, and it levels off, and it's flat there, and then it continues concave down, and it stays concave down until we hit this point, concave down and decreasing, so there it is, continuing, concave down and decreasing. And then what happens is right at 4, it keeps decreasing, but it switches to concave up. So that looks something like this. Since the derivative was undefined there, I'm going to assume I had a vertical tangent. And I think that's the first time we've seen that. So this is kind of a cool one. You get to see the corner, which those 2/3 power, 4/3 power, those are a great example of when you actually get a corner in a fairly simple function. Because if you take just a 1/3 power, a cube root, it looks something like this. And then when you square it, it forces everything to be positive, and you get this little mirror, and that makes a corner. And then the same thing with the vertical tangent line. That's another one that you get with cube roots and fifth roots. Odd roots can give you that. In fact, any root can give you that. Okay, so there's the whole way through with kind of a funny radical function. Thanks for watching.